All right, now we're going to talk about waves. We've talked about energy. Now we're going to talk about another way for that energy to be transferred. So, a wave is a rhythmic disturbance. Rhythmic meaning happens at regular intervals, regular periods, that carries that energy without actually moving matter along with it, which sounds complex, but it's really not. As you can see here, the energy of the people standing up doing the wave goes around the stadium, but the people themselves, they don't move very far at all. They move right there in their seats, up and down, but the actual wave travels all around the stadium. So the wave is traveling, the people are moving very little. That is how a wave carries energy. People move very little in their seats, but the energy travels a long distance. That's what we mean when we talk about rhythmic disturbances. This movement of the person is the disturbance, and this energy is being carried, but the matter, which is again the people, not moving very far at all. So those molecules are transporting that wave energy without themselves going anywhere. Okay, the water molecules here that are actually doing this damage, they didn't move very far at all, but the wave energy itself came from far out in the ocean. So the particles of water didn't move very far at all, although they did move. But since the energy started way out in the center of the ocean, it's not those actual ocean particles that are doing this damage. It's these particles that are doing the damage. So they're not moving very far, but they're still carrying a lot of energy. So the wave material that carries that energy, we call that a medium. It is what actually transfers that energy of the wave from one place to another. So here, obviously, in this kind of wave, a water wave, that medium is the water particles. Here in the slinky, that is obviously the metal of the slinky. Waves can be carried through the air, gases. They can be carried through liquid, obviously, here, and they can be carried through solids. So the medium is the actual material, those particles that are moving. The medium is those particles. And we call waves that use matter or mediums to transfer energy, we call those mechanical waves. And here are the two types we're going to talk about, a transverse wave and a longitudinal wave. First, we'll start with transverse waves. Waves that are called transverse transfer energy by their particles vibrating up and down, even though the actual energy is traveling in a straight line. So the particles are moving what we call perpendicular to the wave motion. Wave motion this way, particles moving up and down this way. We call that at a right angle or perpendicular, and I'll show you what that looks like here. So you see that the wave is traveling, the energy is going this way. But if you keep an eye on just one of these particles, you see they're moving up and down this way, which is once again at a right angle. That is perpendicular. So the particles move up and down this way, but the wave energy goes along this path, and you can see those are at a right angle to each other. That's what we call a transverse wave. And here is an example of one right here. These particles moving up and down. The transverse wave moving along this path. Now the wavelength, that's a way to measure a wave. Specifically for transverse waves, the wavelength is the distance from a crest to a crest, right? Trough to a trough, right? Troughs being the bottom of a wave, crests being the top of a wave. Okay, the wavelength is the distance from crest to crest or trough to trough. That's the easiest way to measure wavelength. Now wavelength is technically the distance from one point on the wave to the exact same point on the next wave. So I could measure it from here to here if I wanted to, but obviously it's very easy to measure crest to crest or trough to trough. Crest meaning once again the top of that wave, trough meaning the bottom of the wave. Most of us already know that though. And here we go. Boom to boom, boom to boom. That is how we measure the wavelength. It is exactly what it sounds like, the length of the wave. Now, amplitude is another way we measure a wave. When we talk about a transverse wave, once again, those waves that the particles go up and down, but the energy goes this way, we talk about the amplitude as the distance from this is the baseline here. The amplitude being the distance from the baseline to the crest. We also call this baseline the resting point. Baseline or resting point to crest, or baseline resting point to trough. That is the maximum distance that those particles are traveling from the resting point. Okay, amplitude is the energy. It's the amount of energy. It measures the amount of energy of a wave. So if it goes up really high, it has to have a lot of energy to get up really high. And if it goes up really high, then it's going to dip really low as well. So amplitude is how much energy that wave has. Very important measurement of a wave. Its energy level. So here we can look at these amplitudes, right? This right here, this line is obviously the resting point or the baseline, right? And this is the distance that that wave travels from the baseline. So we can do here, we can measure the trough. Obviously it drops down to 2. So if it starts at 3 and drops down at 2, I think we know that that's a 1 meter amplitude. And you can see that amplitude again here as it goes from the baseline up to 4. So from 3 up to 4, that is 1. This is a little different. Right here we see that it's about right here. That's our baseline, maybe at about 0.5 or 0.75, and it goes up to about 1.5. So we can see that that one is 0.75 meters, because if the baseline is at 0.75 and it goes up to 1.5, that difference is 0.75. So you can see the amplitudes here can be measured in meters. They can also be measured other ways, but these are measured in meters, and that is the amount of power. If this amplitude is 1 meter and this amplitude is 0.75 meters, then obviously this wave has more power, more energy. And back to mediums, right? We talked about mediums, just to keep you thinking about mediums. This is a wave, and the medium is what is used to travel, use that energy to travel along. And I believe this medium is obviously a piece of string or a piece of rope. That is the medium. It's the particles of the string or rope that are carrying that energy. But you know, if you have a rope tied to a wall and you move up and down very quickly, that energy, you're going to hit that wall. But the rope itself, these particles are not going to hit the wall, are they? These particles are not going to hit the wall. These aren't, but they are carrying that energy. It is these particles at the end that will actually hit the wall. So the energy is traveling through that medium, but this part is not hitting the wall. It is only this part at the end. So the energy goes all the way through the medium to transfer from the hand to the wall. Now we'll talk about a different kind of wave. We've talked about transverse waves. Now we're going to talk about compression waves. The matter in the medium in compression waves moves forward and backward in the same direction as the wave. So transverse waves were in the opposite direction at a right angle or perpendicular. And you can see here, this is a compression wave. Those particles are moving back and forth here in the same direction as the wave is traveling. The wave travels this way, and the particles are also vibrating back and forth that way. You can, spot a particle here, and we'll watch it, and it's just going back and forth, back and forth, back and forth. That's what compression waves do. Compression waves are also called longitudinal waves. So compression waves, longitudinal waves, their particles move back and forth in the same direction that the energy is traveling. Once again, the opposite of what transverse waves do. I like this animation. Once again, a longitudinal wave, the particles also vibrate back and forth along the same path that the wave travels. This is another example of the way you can illustrate a longitudinal or compression wave. You can see they're called compression waves because here the particles compress together, and then here they spread out. Compress again and then spread out. Much like a slinky would do. If you laid it out and kind of pushed on it, it would send that energy down there because these particles would come together in a compression, and then they would spread apart and then come together again. That is how a longitudinal or compression wave transfers its energy. And here you can see that concept of wavelength again. It's the distance from one point in the wave to the exact same point in the next wave. So boom to boom. We've got compression to compression. That is the distance of that wave, the length of that wave. Like I said, in a longitudinal wave, that wavelength, distance from compression to compression. Or we could also do from a point in the rarefaction to the point in the next rarefaction. Boom to boom. So the concept is the same. You measure it slightly differently in a compression wave than you do in a transverse wave. It might be a little easier to spot in a transverse wave than in a compression wave, but it's still the same thing. It is the length of that wave. All right, amplitude, it is very similar in a compression wave as it is in a transverse wave. It is the energy that is in that wave. Okay, so the tighter that compression is, the more energy there had to be in that wave pushing it together. So amplitude can be measured in a longitudinal or compression wave as the tightness of these compressions and then how far apart the rarefactions spread. You can see here that there's more pressure compressing it together, and then when the pressure is lessened or decreased some, they spread apart, which is it's natural. If you're not squeezing them together, then they're going to spread apart. So we're going to talk about two basic kinds of waves. Sound waves being one of them, compression waves. We're going to talk about some sound waves. We're going to talk about those sound waves are compression waves. You can see those compressions right here. And we're going to talk about electromagnetic waves. We sometimes refer to these as light waves, but they are the full waves of the electromagnetic spectrum, which you can see here. And we will talk about those in great detail later. Electromagnetic waves, transverse waves that transfer energy without transferring matter, right? They are a special kind of wave. They don't require a medium because they don't need that matter, right? Electromagnetic waves are special. They transfer energy without using matter. We talked about this in our energy transfer, specifically our thermal transfer last unit when we talked about the light and heat from the sun, the light energy from the sun coming to the earth through empty space. We called that radiation. And this is that similar concept. Electromagnetic waves are transferring their energy without that matter, so they do not need that medium to transfer that energy. And we'll talk more about those once again later. Here's a good comparison between, you got your transverse kind of wave here, once again that matter moving up and down when the energy is going this way. And you've got your compression or longitudinal wave here, the matter moving back and forth, transferring the energy once again in the same direction this way. Okay, and you can see that a rarefaction is kind of very similar to a trough, a dip in energy. And a rarefaction is a dip in pressure. A crest here in the transverse wave is very similar to the pressure of the compression in a longitudinal wave. So they are kind of similar, and you can think of them as very similar parts of these two different kinds of waves. You can see the amplitude differences here are also very similar. This obviously has a higher amplitude wave. Those crests and troughs are much more defined, whereas here they are not. And you can see here that these compressions are much tighter in this higher amplitude wave. There's a lot more space in between the rarefactions. There's tight, then a lot more space, compressed, a lot more space, and then here these are not compressed quite as tightly, and there's kind of, not as much space in between the rarefactions, showing you that there's not as much energy in this wave. The tighter that compression, the harder they're pressed together, obviously that wave has more power. Here's another good example of all these concepts in a transverse wave. Here's your wavelength, here's your amplitude. Here's another word we might use from time to time called displacement. The total displacement is how far that wave travels from crest all the way to trough. And that might be another way to show that energy level that is in that wave. So sometimes we might talk about displacement as well. Wavelength, amplitude. This is good. These are much easier to see in this transverse wave than they are in compression.